It feels very nice to be able to speak in front of people in person and not virtually, so thanks all for coming. Imagine waking up 70 years ago in London on a cold winter's morning. What starts as a normal fog turns yellowy brown. It might be hard to see your feet, and for some people, they struggle to breathe. The Great London Smog lasted 4 days, and it's said that it can have caused up to 12,000 deaths. The emissions that we have in our skies have repercussions. In this case, it was to do with the burning of coal, combined with some unfortunate weather conditions. You might have heard of the CO2 in the atmosphere causing global warming, or we have the chlorofluorocarbons, or refrigerants, causing a hole in the ozone layer. So if our emissions have repercussions, how can we predict and find what the impact of emissions would be before we actually put them into our skies? Well, to do that, we need atmospheric models. On the left here is a satellite measurement. So it's looking at the concentration of ozone, in this case, at different parts of the world. And in this case, ozone is important because in the stratosphere up high, it's good to stop harmful UV light, but closer to us, it's actually a harmful pollutant. So it's good to be able to monitor and look at the concentration of ozone throughout the world. Now, we can try to model this with an atmospheric model. In this case, it's UKCA, and that's the model I'll be using during my PhD. So the really good thing about these models is that they can allow us to predict what would happen if, let's say, we doubled the emissions in industry. How would that affect ozone? Or let's say we want to figure out what is having the biggest impact, which industry is impacting our ozone concentrations the most. Atmospheric models can be used for those things. But they're only as good as what the parameters and the reactions and everything that is inside the model. So as you can see in comparing the left and the right, our models don't completely simulate the reality. And we want to improve that to make them more efficient and better at predicting and assessing impacts. And I talk about ozone, but really this can be done for anything. You can look at different compounds, different pollutants, and they can be used for a range of things. So how do we improve atmospheric models? Well, my focus is on the reactions, as I am a chemist. In terms of figuring out what the reactions in a model looks like, this is a visual representation where the blue lines represent the reactions and the dots represent different compounds. If you can maybe have heard of the lifetime of a compound in the atmosphere. Well, it doesn't just disappear. The carbon and the hydrogen and the oxygen, it just transforms from one thing to another. And the reactions is what connects those compounds together. But again, they're only as good as the current science, and we need to continually improve the chemistry inside to improve our models. Because this is a general audience, I'll go through what type of reactions occur. So the typical reaction would be to do with collisions. My example here is methacrylene. It originally comes from a tree-based compound. And so a collision would be with something like an OH radical. There aren't a lot of these in the atmosphere, but they're really, really reactive. So when it just happens to collide with methacrylene in the right spot, it might react to form water and a methacrylyl radical. In this case, when I say radical, it means it's reactive, and you'll see that it'll transform and form different compounds later. But again, that started off with a collision. The other type of reactions, the things that I find really interesting, is the sunlight-based reactions. So in this case, instead of a collision, methacrylene will absorb some sunlight. And depending on what energy it absorbs, if it's enough energy, it has enough to split apart. Essentially, it's vibrating so much that it just falls apart. And that is another source of reactions that are also in our models. In terms of my PhD project, initially my aim is to improve and add new sunlight-based reactions into the models, because if we can improve those and get them closer to the reality, we'll improve our models. However, what I'm going to be talking about for the rest of this talk is something I did research on in my previous institution that I found really exciting. So I talked about sunlight-initiated reactions and collisions-based reactions, which is what we think about and what's included in the models. Whereas now I'm going to talk about something a little different. So it is starting off sunlight, but we call it atmospheric photothermal oxidation. That's a mouthful, but I'll explain what it actually is. So initially, methacrylene can absorb light, but instead of it having so much energy that it falls apart, it just keeps that energy. So it's vibrating and has energy, but not enough for it to break apart, but enough for something like oxygen to come along and react. And I should say that when oxygen and methacrylene are together, they're stable. They can be together for a long time and wouldn't react. But it's the extra energy that we get from sunlight that will allow this reaction to happen. Now, again, the cool thing is it's kind of a mixture of the sunlight-initiated reaction and the collision-based reactions that we have in the model, but this isn't really included in the literature for atmospheric chemistry. So let's look a little bit into what evidence we have for that. And so I want you to focus on this HO2 radical, one of the products, because that's what I looked into. And I said a radical is really reactive, so it's hard to look at, but I use a specific experiment that will let me observe this radical. And so what you can see here, and I'll explain it, I'm sorry if it's intimidating, but what it is I have methacrylene and I have oxygen, and then I'm going to shine a light onto it. And I should say that the energy of light that I have, currently, according to the literature that is there, it shouldn't form any HO2 radicals. So really, according to the literature, I shouldn't be forming anything. But when I have methacrylene and I have oxygen and I shine a light onto it, I did see HO2 radicals form. And it happened that if I double the amount of methacrylene, I doubled the amount of HO2. And so for me, that was really cool. That was when we did this experiment, for us, it was a smoking gun. This reaction is happening, and it's something that isn't currently in the literature. But if you need a bit more proof, and also saying, well, it's one thing for it to happen, but is it actually important? You know, is it significant, or is this happening 1% of the time? Well, this type of experiment lets me look at the products. And so in this case, I have methacrylene and I have no oxygen initially. I shine a laser at it, and at this energy, this is the product. And if you're saying, what am I looking at? Well, there are a few peaks, but in this case, there are artifacts of the experiment. And what we're looking for is any other peaks that will represent products. If I made a product when I had shine light at methacrylene, I would see them pop up, and in this case, pretty much wasn't. And so in the same way, instead of just having methacrylene and light, I'm going to add oxygen. Now, I want to remind you that methacrylene and oxygen together, nothing happens. I've done those studies, nothing happens with methacrylene and oxygen. However, when I have light, methacrylene, and oxygen, which is that, remember, that special type of reaction, I saw a great number of products appear. And so this is the complete same conditions, the same intensity of light, the same energy of light, and it shows that as soon as I add oxygen, I can see those products appear. And so for me, this was exciting, and it said we have a new type of reaction in the atmosphere that we don't really fully include and fully think about. And so in this case, it was for methacrylene. A PhD student in my group at the time did it for another molecule, formaldehyde, and really there could be a range of molecules in the atmosphere. Well, this reaction isn't included, but it should be. And so coming back to why this is important, well, I want to improve atmospheric models. And in my PhD, I'm going to be looking, assessing, and updating sunlight-initiated reactions in atmospheric models to get them closer to reality. So by exploring new types of reactions and exploring how that affects the chemistry in the atmosphere, I can get my model, my simulation, closer to the satellite measurements, closer to reality. And hopefully that will mean that we could better predict what will happen when we change the emissions, or what will happen, or what we can do really to improve the air quality and improve our way of life. That's my talk. I would like to have a few acknowledgements in terms of the people in my first experiment where I looked at HO2 radicals. That was done by Isabelle Weber and Christa with me in France at Lille, and the rest of the experiments were done at my former institution, UNSW, with my supervisor, Scott Cable. Thank you so much for listening, and I'm happy to answer any questions that you have.
Thank you very much for this wonderful talk. And I'm turning to the audience and to the jury. Does anyone have any questions? Please feel free to ask. Just put up your hand and I go there with the mic. Or if the jury has any question, please use the microphones on the table.
Thank you, Ellery.
this is on. If you're modeling one specific kind of reaction, how many different reactions do you think there are that you need to incorporate into your model?
Well, that's a good question, because it can get really, really complicated. And in some models, what they try to do is they try to simplify and say which reactions you really want to care about. Because when you have, 4 to 14,000 type of reactions that you can put in there, there are different models that are being developed saying, okay, well, the one that I showed previously, that has pretty much all the ones that they can think of. And then there are models where they try to make it as small as possible to increase computational speed, because it definitely takes a lot longer. So yeah, a lot of reactions. And so in terms of photolysis reactions, sunlight-initiated reactions that I'm looking at around close to 100 at least. Yeah.
Thank you. Okay. I think Ada was before you. I will have a good exercise today, I see.
Hi. I was wondering why we care about methacrylene. Is there a lot of it? Is it specifically interesting for another reason?
Yeah, that's a good question. And there is a fair bit of methacrylene. So I don't know how much you know about the chemistry of trees, but isoprene, so pretty much when a tree is stressed out, so things like drought or hot temperatures, a lot of sun, it can emit isoprene in the air. And roughly, I think 20 to 30% of that isoprene becomes methacrylene. And so because over trees, there is a lot of it, so it is something where there's a lot of it in the skies, and understanding its chemistry means that we generally improve the chemistry of the atmosphere. But it's the cool thing about, that's why I studied it specifically, but with this reaction, again, this reaction could be happening for a whole range of different species. Yeah.
Thank you.
Okay, I'm running to the other question.
So what is the relationship between the wavelength of the light and which chemical reactions happen? And
Oh yeah, cool. So that's a good question. It's in a way twofold. So there's two things that needs to happen. First, it needs to absorb light, and not everything will absorb every energy of light. And secondly, I guess the light needs to be there. So sunlight, is absorbed by ozone. So there are some energies where a lot of reactions would happen, but that light just doesn't reach the troposphere or doesn't reach where the chemistry would happen. And thirdly, and I guess this is where your question comes in terms of you need energy to break bonds. And some things are easier to break, some bonds are easier to break than others, and some reactions happen easier than others. So depending on what energy of light, depends on what type of sunlight-initiated reaction can actually happen. So look at methacrylene, for example. Depending on the energy of light, you could have 4 things happening, like 4 different types of sunlight-initiated reactions, or when I was looking at pretty much only 1. So that's why the energy of light is important.